until it starts recording. Okay, it does. All right, so let's continue on. We've been discussing a lot of the core side. The core side means that the CPU side, that whatever is on the compute core, right? Fetch, decode, execute. We haven't talked about memory, and then we talk about write back. So we will talk now, basically we'll shift our focus from something done to the compute instruction into something that is actually like a bottleneck in, I would say, every single program, almost every single program. This has become the main bottleneck and the main reason why you need to keep buying newer and newer hardware. These are the main memory, how to manage them, how to deal with loading the memory, how do you actually make it faster. Today, we are actually focusing on how to make the memory faster by caching. And then we might go on, depending on how far we are on the discussion, we might move on to the discussion on virtual memory as well. So that's what we are going to discuss today. Give me 1 second before my cat eats my charger. All right, I'm back. Yeah, sorry, she just woke up, so that's what happened usually. Whenever she just woke up, she just run around a little bit and she go back to sleep. Anyway, a quick announcement. Office hour, I changed it to 4 to 4:30 because of the conflict. I'm so sorry. One of the students that I mentor, he has a new semester come in, and there's a class conflict everywhere in my schedule except for that slot. So I'm moving it to 4 to 4:30. You can still request additional office hour, but and you know this, whoever did this, you know who you are, because you asked for office hours twice, and I make time for that with basically 2 hours of my life. Which, let me put it this way, my schedule is so bad this semester to the point that the only day I have a slot for my lunch is today. The rest, I have meetings during lunch hour. This is how bad my schedule is. You ask for office hour twice on the same week, you never show up. This is not professional. This is bad. I'm still okay with additional office hour. 2 things I really ask you to do is, if you do that, show up. It's bad. No matter how you put it, this is really bad. You are asking for someone else during the work hour, and that person is super busy, and then you not show up. Don't expect leniency from me if you do this. The next time, if you do this again, your late days that I told you, everyone have 5 late days on all the assignments, those are gone. Because you're not respecting everyone else's time. I'm not going to respect your late days. This is my new policy starting from this day. If you do this again to me, for any one of you, your late days are gone. Understand? Don't do this again. All right. One last thing. I've got some questions about how to run SM2X, right? And it turns out that I'm not sure you know how to use Unix-based OS, such as Ubuntu or Linux. So I don't. So basically, these are like freshman material if you're doing computer engineering or computer science. And if you are at that position, I'm sure you forgot. It's most likely that you forgot what you learned. It's a long time ago, right? So you need to refresh what you know. And you need to do it now, because this is going to impact your project. This is going to impact the assignment going into the future. You need to know the basic command, and you need to know how to actually do certain things by Googling certain keywords. If you can't run a command and it says permission denied, if you Google that, it will tell you how to solve it. You don't need me for that. If you need me for that, I'm going to send you a Google link that actually answer that on Google search. Your job is to go to my Google search. I'm not going to go any more than that because this is like a prerequisite to a master program. If you don't know this much, I'm not sure why you're here. I'm not sure even why you graduate. Who graduated you? I don't know. Where did you get a degree? I don't know. They're not competent. Like, you need to know this. You need to know how to solve these like super basic things. Otherwise, you're gonna have a lot of trouble in my class. And I'm not gonna be lenient for you. This is basic. If you want to be any engineer that has to deal with computer, you need to know this. That's why it's in every single computer engineering program, freshman class. You need to know this. All right. So now that I put in all my rage and concern, the rage about office hour part and the concern about the hey, please know some Unix-based OS and know how to use it. If you still have question, I don't mind answering that. But again, if you are at that point in your career and you want to still pursue computer-based career or IT-based career, you need to figure this out. I cannot see how you will survive in the world. You are going to be easily replaced by anyone who knows how to program. It's that bad. All right, so that's it for the announcement. We moved the office hour. I still am okay. So basically, I shrink to half an hour because I realized no one used, like we haven't used more than 20 minutes so far. And if you need more, just let me know. I don't mind making the time for your slot. But if I do make the time, you need to make your own time for that too. We need mutual agreement on that. So everyone agree on the policy? Yes? Okay, cool. Again, if you do not show up for your own makeup office hour, your late days are gone. All right. Okay. So let's continue on to the content of this class. Now that we have this formal handshake about the new policy, that hopefully make my life a little bit less miserable in terms of scheduling. I want to quickly review what we covered so far about memory hierarchy because we just had 1 week of review, 1 week of the exam. So the last time we talked about this was 3 weeks ago. So let's refresh what we know so far. So from the programmer point of view, if you are buying the memory, this is what you want. You want your DRAM to be unlimited. You want, instead of 16 gigabyte of DRAM, 32 gigabyte of DRAM, you would be curious, like, why can't I have unlimited DRAM? Why can't I have 10 terabytes of DRAM or petabytes of DRAM, right? That way, you don't have to worry about the memory capacity ever. You can train all this complex deep learning with a lot of inputs, a lot of data set, and somehow it still would work on a GPU. Somehow you can train it on one single GPU. In fact, capacity is now one of the major bottlenecks in machine learning application. That's one of the reasons why you have to, like, sometimes you have to upgrade your GPU to train a much larger model. Because the performance of this thing called unified memory that NVIDIA is proposing is still not good enough. It's still ongoing research on how to manage it. I actually, on my own, I published a few topics. And if you're curious about this, I'm one of the person in the world who can actually tell you what's going on. I'm one of the only few people in the world who can tell you what's going on over there. The other problem is you want this to be contiguous, right? How many of you run the program, multiple programs in a row, basically at the same time? How many of you have Chrome tabs that has at least 5 tabs opening at the same time? Everyone, right? Including myself. Like, to be honest, right now, once I'm done with this, whenever I need to work, I'll have some Chrome tabs opening. Some of them will be Google search. Some of them is like overleaf. I'm modifying a paper, right? So These tabs, if you do Control Alternate Delete and check the Task Manager, if you use Windows or if you run top on Linux, how many of you realize that there's going to be a bunch of process called Chrome on your Task Manager? The reason behind that is each time you open a tab, each time they have to load a PDF, each time Chrome has to do something. The way Chrome is programmed is actually super multi-threaded and multi-process. So they actually spawn a different process. These process is each of those Chrome lines. One of them would be responsible for rendering what you want to see on the screen on that one tab. The other one would be rendering the PDF, right? It's a totally different program built as a part of Chrome that render the PDF. The other program would be rendering the active parts in your website that you're seeing, right? So those things, if you think about it, how many of you programmed in C before? I believe everyone here, because you have to do assignment. I forgot about that. So you have used malloc before, right? The one that allocated memory. How many people annoyed by the fact that you have to multi and somehow you have seg fault? Please raise your hand. That I'm raising my hand right now because I do. Okay, so if memory is not contiguous, whenever you have these processes running at the same time in parallel, not just being able to keep track of malloc and free, you need to keep track of who else used that chunk of memory. Is that process using the memory at that address right now? Can I allocate that? So you want your abstraction whenever you use an array, right? Let's say you define, say, A 1 million. Basically, you're creating 1 million integer. You want address of A1 to be next to A2, right? You don't want some random address that sits in the middle between A1 and A2. You want to be able to move from one element to the next element in a contiguous pattern. So that's what you want in the abstraction of memory. But if you think about it, whenever you buy DRAM, it's a singleton thing. It's one thing. Start from address 0 to address whatever the capacity of your DRAM. You might have realized this in the assignment already, right? The region for your data start at one place and at another place. It's one big thing that's shared across all the program. And that's big. The abstraction to having each program has its own contiguous block of memory, while they share this one single physical memory, is you need something to handle that. So basically what I just talked about is this bullet, right? Think about what happens to two programs running concurrently and perform a lot of allocation and deallocation. We'll cover 8 and 9. I'm hoping we can cover some of this in this today's lecture. But programmers see the virtual memory. Every single address that you've seen up until assembly code, those are virtual memory. What you see in our lab, those are physical memory. So whenever you deal with pointer in C, those are all virtual memory. Whenever you see the address in your assembly code, that's also virtual memory. The OS and the hardware, they work together to translate that virtual address into a physical address, the actual location inside your DRAM. And we'll learn how that works. Inside the hardware, think about it this way. Whenever you buy DRAM, whatever DRAM you're buying and plug it into your motherboard, that thing are physical. So what else do we want in the memory? We want them to be fast, right? We want them to be magical. Sometimes if you want to get an address, it's there. You want unlimited capacity, as I said earlier, and you want them to be free. And these are magical. You also want unlimited bandwidth. The more you want to access the memory at the same time, somehow I hope my memory can handle that, right? And the way DRAM is built, is to optimize for all the three things here. But if you think about it, All these things conflict with each other, right? If you want a fast memory, that probably would cost more. If you want unlimited capacity, it probably would cost more. If you want unlimited capacity, anyone want to guess how does latency go? The speed at which you get the data. Is it going to be the same? Is it going to be slower? Is it going to be faster?
Slower.
It like
Should be
most of the
lower.
time it's going to be either a little bit slower or quite slower. The reason behind that, think about it this way. Let's say you buy a house in the village. It probably take a few minutes to find where your house is, right? Because a village is a smaller unit compared to a city. Right? A city can have a lot more houses. It's bigger. It has higher capacity per unit area. But then there's so many addresses, so you need to actually go and search. So you spend more time searching for those. There are multiple ways you can organize the city so that it takes almost the same time as going to find that house in the village. But still, there are overhead associated with that. So when we go to the DRAM lecture, we'll cover all these things, right? And we'll cover how do we actually organize the DRAM such that you get as much benefit as possible without too many costs behind it. There's a trade-off between SRAM and DRAM. I'm not sure if you heard about the two terminology or not. SRAM is whatever you use in the cache. So when you buy a CPU, what do they tell you when you buy a CPU? The clock speed, right? For sure. How many cores do you have? How many of you notice there's this thing called cache? When you buy a CPU and look at the spec sheet, this thing called cache, we'll learn about it today, and we'll learn why they are so important to make your CPU fast. This cache consists of SRAM, static random access memory. They are fast. They are typically a lot smaller than DRAM, which is what you buy when you buy this memory. That memory stick that you buy and plug into the motherboard, or the DRAM that goes in your phone, those are all dynamic random access memory. They are typically cheaper in terms of capacity per dollar or per baht or per euro, whatever unit of money you want to use, but they are slower, right? The reason behind that is SRAM use 6 transistors. DRAM, 1 transistor, 1 capacitor. Having 6 transistors allow you to keep the charge. Basically, the transistor is organized in a way that it's going to forward the charge inside the loop, in the circle. So electron never move out until you want to move them out. Then you write to the cell, right? A unit of SRAM and DRAM, we call it cell, right? What is a cell in English? I guess one meaning of that is like biology like term, but you use also a cell to hold human, right? To cage them. So SRAM cell and DRAM cell. SRAM cells consist of 6 transistors. DRAM cell consists of 1 transistor, 1 capacitor. And the way it works is SRAM would have something like this. Basically, they would forward. And this would be another transistor that comes in and read the signal, right? So this is 2 transistors here, 1 transistor here, 1 transistor here. This for reading and writing. And these 4 transistors just to loop the electron around, to keep them in here. Whenever you are not writing, you can read what's the value of the electron, like how many electrons are there, so you can measure is it 1 or 0. Over here in the DRAM is something that looks like this. So you have an access transistor that comes in, and here's a capacitor. So, and this is ground. Basically, you keep the electron inside the capacitor. Inside the capacitor. You can have gigabytes of DRAM versus megabytes of SRAM in your CPU. SRAM, if it's really small, it's actually like sub-nanosecond. What you see nowadays are 1 to 3 nanosecond. If it's 1 nanosecond, if you have 3.3 gigahertz, how many cycles is that? What's 10 divided by 3.3? Around 3 cycles, right? So you look at spec sheet these days, Intel CPU, your access latency of the first level SRAM cache is around 4 cycles. That's how much time it takes to get your data. DRAM, these days, if you look at DDR4 or DDR3, actually DDR4, let's just say DDR4, there's no DDR3 anymore. This slide, the data is back in the DDR3 age, but still the latency is roughly the same. Something like tens of nanoseconds to like 50 of nanoseconds, depending on how you access it, and we'll go into detail later. The reason why you want to care about this different number is when you program, you can actually make the program more friendly to DRAM. There are multiple tricks you can do. We also cover some emerging technology. You can have DRAM. So when you buy the DRAM, right, it comes with a stick and then the chip. But these days, we can actually put a chip on top of a chip on top of a chip, so you can stack them together in the 3D manner. So you have more capacity and more bandwidth. And you can also have this thing called NVRAM that is a lot more capacity. You're looking at terabytes of memory, and then it actually uses less power. It consumes less power. So a lot of these low power design, sometimes they also look at NVRAM as well as an alternative to DRAM. So let's be greedy now that we know, now that we know some of the content of what goes into your memory, right? We want both fast and large memory. So what we covered so far, SRAM and DRAM, what is fast? SRAM, right? So, and what is big? DRAM. So to get the best of both worlds, right? To actually be greedy, why can't we use a combination of those? Basically, have multiple levels, right, of memory. This is called the memory hierarchy. And you start with a really, really small level 1 SRAM cache. Then you have a small, relatively small L2 and L3 SRAM cache. In a large data center, these days you have a L4 3D DRAM, L4 3D DRAM on the chip as the level 4 cache. And then you have a large DRAM as the main memory. And these days, you look at data center, you can have non-volatile memory at the end, because those are the biggest, but they're a little bit slower, as the core main memory of your machine. So it's actually totally normal these days to expect machines in the next few years to have terabytes of memory. So those are normal. And at least I'm pretty sure they'll come out really soon. And this memory hierarchy is something like this. You have a CPU core. So what we covered so far is inside this thing. The fetch, decode, execute, the pipeline, branch predictor, everything is in here inside the CPU core. When you have a data access, they go to the L1 cache. Right? They go to the L1 cache. So if you consider the timing we said earlier, let's say it used 1 nanosecond, how many cycles it would take for the memory stage in the pipeline? If you have a 3.3 gigahertz clock, how many cycles is my memory stage in the pipeline? 3, right? Around 3-4 cycles, depending on the clock, depending on how fast is the cache. So your pipeline from 5 stages becomes 9 or 8, depending on how many stages you add. Then you can access the memory really quickly. It's much better than 50 cycle, right? It's much better than 50 cycle, which is about 12 nanosecond. Then if your data is not in the L1 cache, you go search these share L2 cache. So the L1 cache, typically they are private to each CPU. So let's say you have, you buy AMD Ryzen that come with 6 CPU. Each of those 6 CPU come with its own L1 cache, and they typically have this share L2 cache that is backed by the main memory. You can have L3 cache, L4 cache in the middle as well. That's also totally fine. The reason behind this, I'm gonna compare this to let's say I want to buy milk, right? Or I want to get milk. Basically, I want to drink some milk. What do? Let's say I'm here right now in this room. What do I do if I want to get some milk? I'll first head out and check my fridge, right? To see if there's milk there. Think of a fridge as your register files. I'm gonna check R1 is my data there. And then I realize with sadness that, okay, my data is not in the fridge. So what's the next step if I want to buy milk? What would be the easiest thing I can go to? Easiest place? I will go to 7-Eleven, right? Which, if you look at Bangkok, it's everywhere. And hopefully they stock some milk. And actually, most of the time, treat this as an L1 cache, right? You go to 7-Eleven, which hopefully is just across the street or a few blocks away. Basically, a short walk to the milk so that I can buy it and I can consume it later. I'm going to bring the milk in to my fridge. Basically, you bring the data in to my register so that I can consume it. Then if somehow the 7-Eleven next to me doesn't have the milk that I want, somehow, I don't know, most of the time they would have it. And in reality, if you look at an L1 cache, you're looking at like 90% hit rate. Most of the time it's there. But if they're not there, I would then have to go to like Lotus or Big C, right? The bigger supermarket that likely would have milk, right? Likely would have milk. And the way they stock it is basically there'll be a stock coming in, there'll be a shelf for the milk, right? Because a lot of people buy milk, they're gonna keep restocking that, but sometimes they can run out. So I'm sad again, they ran out of milk. There's none in 7-Eleven next to me. There's none in the Lotus in the location that closest to me. What do I do next? What I need to do next is I'm going to keep searching further and further away, right? It's like you go to the main memory. Think of main memory as a much bigger supermarket that always stock a bunch of things, right? It's like maybe a supermarket that are bigger size in the city. So it will take more time for me to go there. How many people sometimes get data from the hard drive? You do it a lot of time, right? Or through the network. Think of it as instead of going to buy your milk from the supermarket, you go to buy your milk from a farm. That's how far it is. If you look at hard drive access latency, it's microsecond versus nanoseconds. It's 1,000 times worse. So in computer, whenever you program, try your best to avoid using this disk. Put them in the memory as soon as possible. You don't. A lot of time to speed this up, you might even spawn a different thread to load the files while you're doing something else. So these are the concepts behind memory hierarchy. Sorry for getting sidetracked, but I love this analogy because it's actually true to how I use the data. It's the same as how I would like to drink some milk, or I use the milk for my coffee, and then I'm sad because the milk is not in my fridge. How would I go get it? So caching, essentially how you store or stock the data inside a unit close to your core, right? it takes advantage of two things. The first thing is temporal locality. If you haven't heard about it, please be mindful of this thing when you program, because these can make your program a lot faster. So how many of you program it? You program your code this way? It's kind of like asking you how many of you use a loop. How many of you use a loop before? A for loop. Everyone uses it, right? How many times this variable I and n are being used? All the time, right? This is called temporal locality. If you are using something, it's likely that you're going to use that same thing again. Right? It's really likely that you're using something again. And how many people do something like this? Inside the loop, you are going through the different element in your array and doing the copy. This is called spatial locality. Spatial locality means, let's say you use A0. It's likely that you're going to use something like A1 next, or maybe your trend would be A0, then A2, and then A4. Something close by, basically. Some data close by to what you just accessed. And this is normal, right? This is normal way to program. So both of these are our observation. There are two papers back in the 1960s that take advantage of these two characteristics, basically. Put the data that are likely to be accessed again close to the CPU. Back in the day, they haven't called this a cache yet, but structurally they are cache. They are the cache as we know it. Temporal locality has to do with you use X, you're likely to use X again. Spatial locality is if you use X, it's likely that you're going to use X plus 1 and then X plus 2 and X plus 3. So know the difference and know how common they are, essentially. So if you look at the cache, any question about the cache anyway, by the way, any question about why is there a cache, or how that we'll cover how caching works, but you know the benefit, at least, that you want it to be there. It's going to be really fast, and hopefully your data access is as fast as most of the ALU operations like multiply or add. So you can do it manually, and hopefully this is not the case. Programmer basically manage the data and tell what go into my cache. This is called a manual management. This is going to be painful for you because somehow you need to know, okay, this is the data that I need. This is the data I need. It can be useful if the programmer know what they're doing. And this is actually important for GPU performance. So if you need to program something in CUDA, there is an area called shared memory that you can manage the data. You manage what go into your cache so that you have much better usage of that cache. In modern day computing, almost all processor, automatically manage the cache for you. Basically, the hardware perform this management. You as a programmer only just program and deal with the memory reference, dealing with the pointers. But basically, knowing how the hardware manage the cache can make your program faster. Basically, knowing how you would like to access each element can actually make or break your program. How much faster? It can be like 5 times faster, 10 times faster, depending on how good you are at managing this data. So hopefully you know some motivation behind why we want caching, right? So let's go into what is this automatic management of hardware cache. So let's first go to some basic terminology. Recall the load instruction. the first thing I need to ask you is, what's the size of a word? What is a word? It's a collection of bytes, right? That together consists of contiguous bytes that is specified by the how many bits the machine is. Like 32 bits, a word is 4 bytes. 32 divided by 8, right? 32 bits. 8 bytes is 1 bit. 8 bits is 1 byte, so that's 4 bytes. 64 bits, sorry. Then a word is 8 bytes. So the size of a load and the size of a store, it can go up to 8 bytes in a 64-bit machine, right? Caching also has its own unit of data. It's not a word. It's actually bigger than 1 word. This is called cache block. Right? This is the terminology, so please remember the term. Sometimes we call this a cache line. So cache line and cache block, they're the same thing. Each cache block is mapped to some location in my cache. For example, if I want to buy a milk, there will be in a shelf that stock the milk. Right? They are not going to appear at the shelf that stock the food. They're not going to appear at the shelf that stock the snack. There'll be a shelf for the milk, so they can go and know exactly where you have to go. The same thing goes with caching. A block is mapped to some location in the cache. And the cache access is just going to that part of the cache block, so you can get your data and walk out. So when you have a load or a store, it's called data lookup or cache lookup. You literally look up the data. A cache hit means the data is found in the cache. Right? A cache miss, it means that the data is not in the cache. So far, so good. All right. So here are your design choice. Right? The first thing that you can decide is what you want to store in the cache. Do you want to store instructions because you're fetching something from the data, right? You're storing data. Are you storing this translation? In fact, if you look at the caching that we have in the CPU, we have one cache for the data, one cache for the instruction, and a separate cache for this mapping between virtual address to the physical address. We'll go into these in detail. The second design choice is, how do you place the data in the cache, right? Because depending on how you organize the shelf in the 7-Eleven, sometimes you can stock more things that are easily accessed and used often, right? So what can be some items that is bought really often in the 7-Eleven? Water, right? A bottle of water is probably getting bought a lot of times. Snacks or things like ice cream. So these are going to be stocked often, and you're going to make sure they have water, right? Every time you go to 7-Eleven, you can expect that you can buy water. They know about it, so they're going to keep stocking water. Things that are accessed less often, sometimes in there, sometimes not in there, right? There's a time when I went to 7-Eleven and want to buy like paracetamol, and I have a hard time searching for that. For some reason, they don't have it in that particular 7-Eleven, so I need to go to a different one, right? Because it's used less often than water. So another thing is when the cache becomes full, because it's only a small unit of data that you can store, right? How do you pick what to remove? Think of it this way. You are also, again, managing 7-Eleven. Your store is small. You need to decide what goes into your store and what are you going to stop putting in, right? So that's another design decision. How to deal with writes when there are many other cores that want to access the cache. And also many layers of the cache. So we'll talk about this in later lecture. on cache coherency and the granularity of management. Do you want to manage a large block of cache, small block of cache, or multiple granularity? We are not going to talk about this in detail, but be aware that these days there are work that look into, okay, do you want to treat a cache block as a big unit or a small unit or a combination of both, because each data structure prefer different method. Actually, I have a project with a student in Zurich that has data on, like, for example, you look at graph data, you want smaller granularity, but if you are looking at something that goes through the data quickly, such as a matrix multiply, then you want a large granularity. So depending on this, you might want to configure this a little bit. It's a policy that you can modify how you manage the cache, right? Think of it this way: we are the hardware designer now. We are almost like can modify everything. We can modify the software, you can modify the hardware, you can come up with your own hardware. So let's go through something primitive, something that is like a textbook cache design. The first thing you need to consider is what we call a tag store. The way to search if my data is there. It store all the tags, and whenever you have a load or store, basically whenever you want to access the data, you use the tag to see if they are matching or not, right? Just for example, if I want to go buy milk, there are multiple brands of milk, right? Dutch milk, Chok Chai, what else? And now I brain freeze, only came up with 2 brands. But let's say I am really particular about a certain brand. I need to buy a Dutch milk, right? So I need to use that as my tag. I need to compare with a Dutch milk that is 0% fat rather than the 2% or whole milk. So I use that as a tag. I'm not going to buy the whole milk, right? Because I know I want the fat-free milk. So these are what it meant for the tag. I know exactly what I want to search for. I'm going to compare the tag and make sure they match before I buy it, before I get the data. It tells whether the data that you're searching is in the cache or not. And that's what data store, the shelf itself, right? You have the tag and you have the actual data, the one that you're getting. This is where the data is located and it's limited in size, right? So basically, when you have the address, this is used as an parts of the address is used as an index to tell me that's the shelf I want to go to. The other part will be used as the tag. It tells me, okay, that milk is the fat-free Dutch milk brand. So I know that's the one I want in order to retrieve my data. So what's in the tag store? The first, obviously, the valid bit. If it's 1, data is there. If it's 0, data is not there. Whatever tag you see is junk, right? That's a tag bit. Obviously, you need to store the tag. Right? You need to store the tag. And we'll go into more detail of what it means to get the tag, get the index. It would also have the way to represent how we are going to replace the items in my cache. So this is the replacement policy bits. We'll talk about this later. Depending on the implementation, sometimes there's only 1 bit. Sometimes there are a few bits. Dirty bits. What if I write to the cache? Whenever you write to the cache, that cache becomes dirty. You need to propagate the writes to everyone else. Every single CPU need to see the same data. So you need to tag the data as, hey, that data is dirty. If someone else needs to use it, they need to see this updated data, not the old one. For both of these we'll talk later. Both of them has to do with writes. Both of them has to do with what if another CPU need that data. And here's the organization. A cache contains multiple blocks. And I'm sorry, this is really mechanical so far, and it can be really boring. I understand that, but I want to make sure you got the terminology. A cache contains multiple blocks. Each cache block belongs to a cache set. A cache set is, as the name suggests, it's a set that consists of unique cache block. Each memory address is then mapped to a certain set. These are the example. In here, there are 16 cache blocks from 0 to 15. There are 8 cache set 0 to set 7. Over here, block 0 and block 1 belong to set 0. Block 2 and block 3 belong to set 1, etc., etc. So let's say I have an address. Each address is going to uniquely map to only one of the set. For example, this one will map to set 4. You look at the address, you know exactly what set you'll be looking. In this case, let's say set 4. Then you're going to search. Is block 9 the one I need to access, or is it block 8? If it's, for example, if this is what you are searching for, cache block 8, and you're going to get the data, return the data, return the data back to the processor. And yay, you found the data. If block 8 and block 9 doesn't contain your data, then the address would go to next level of the hierarchy. If this is L1, it would then go search the L2. If this is L2, then go search the L3. If it's in L3, then it will go search the DRAM, and the data would be in DRAM, right? So let's do some example, right? Let's do some example. Can someone give me the size of the cache? Some size. Hopefully divisible by 2 if you will, so that we can have a easier time dividing. 16. Let's say 16 kilobytes. How many sets do you want to have? 8 sets. Let's say this is a 64-bit machine. So the data word is 8 bytes. How many cache blocks are there? Actually, there's one missing information. Can someone figure out what's one of the missing information here to figure out how many cache blocks are there?
How big the cache block is.
Yes, how big is a cache block? So let's say a cache block is 64 bytes. Cache block is 64 bytes. How many cache blocks is in my cache?
250.
256. And cache blocks. How many cache block is in a set?
$32.
Yes. So if on the exam, I have some of these number, hopefully you can tell me the rest, or you can tell me what is missing. So this is how you can get the actual organization for the cache. If I have 32 cache block per set, if I'm going to do a brute force way, I'm going to search each cache block in the set one by one by one by one. How many comparator I need for this? How many times I need to do the compare? Tab equal the cache blocks. tag in a brute force way. $32, right? You need to compare every single one of them. So this is 32 comparator. In reality, you can kind of like do it in a tree manner. So it's not 32. In reality, it's cheaper. Okay, so if you're curious, we can go through that in the next lecture. Just tell me how that can be done. If it's on exam, I'm going to tell you a little bit more information on how I would like to implement this comparator, so you know roughly how you would proceed on that. So the more cache block in a set, it means that becomes a little bit more costly, right? You need to spend more comparator, but you can store more things as well. So let's go through the same example. 64 kilobyte cache, 8 sets, 64 byte block, which has 256 cache block total and 32 cache block per set. Give me a random virtual address. So I can tell you how to access my cache. All right, 0x some hex number. How about this? 1, 2, 3, 4, 5, 6, 7, 8. Let's do this. 1, 2, 3, 4, 5, 6, 7, 8. This is, let's say this is your address. So there are 3 pieces of information you want to extract. I'm gonna go through this one by one. There'll be a slide on this, so there'll be a detail on how to extract this. Basically, the address, the way you figure out how to access the cache, it breaks down into 3 chunks. The last part is the tag bits, and then there's the index bits. And then what I would call this is the byte inside the cache block. What does the last part mean? It's basically it tells you which byte you are accessing inside the cache block, right? Because the address is byte granularity. You can access each individual byte, which means that if it's 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, what is the bits that represent the byte in block? If my cache block is 64 bytes, first of all, what is log 2 of 64? 6, right? 2 to the 6 is 64. So basically, you need 6 bits to tell all the unique bytes inside my cache block. So I'm going to say this is bit 0, this is bit 5. Those are my byte in block cache. And there are 8 different unique locations for the cache set, because there are 8 sets, right? There are 8 sets. So how many bits that I need for the index, which is used to tell what set you're accessing? How many bits are there? There are 8 sets, 8 different unique locations, which means you need 3 bits, right? You need 3 bits to tell all the 8 different locations. Bit 6 to bit 8. The rest, bit 9 to bit 63, those are the tag bits. Those are the tag bits. So given this information, I'm going to go through the next slide so we have a clean like whiteboard, basically. So we have address 0x 1, 2, 3, 4, 5, 6, 7, 8. These are your address, right? Bit 0 to bit 5 is the byte in block. I'm going to just say BIB. Bit 6 to bit 8 is the index. And then these are the tag. 1, 2, 3, 4, 5, 6, 7, 8. What are those? 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0. So that's a 1, 2, 3, 4 part. And let's assume the rest are 0 because, wait, is it 8? This is only 4 bytes. If you have 8 bytes, let's assume the rest are 0. All right. 0, 1, 0, 1, that's 5. 0, 1, 1, 0, that's 6. 0, 1, 1, 1, that's 7. That's 1, 0, 0, 0, that's 8. The first 6 bits over here, these are the byte in block bits. The next 3 bits are the set bit. So set bit is 0, 0, 1. These are the index bits. And the rest here are the tag bit. So what's my index? 1, right? Index bit is 0, 0, 1. What does it mean? It goes to set 1. These address get mapped to set 1. What is the byte inside the set 1 that I'm accessing? This is 1, 1, 1, 0, 0, 0. What is that number?
56.
56, yes. The 56 byte inside whatever is in set 1 that has these particular tag. What is the tag? Whatever that number represents, basically, you go look into set 1 and see who has that tag. What cache block has that exact same tag? If they do, you go get the data. If they don't, you then search the next level of the cache. So the process of a cache lookup, right? The process of a cache lookup, basically an address is divided to multiple sets of bits. There's a tag bits that I just show you. There's an index bits that tells the actual set number. And then to get the index bits, each address point to a unique byte. So you have inside the cache block, first of all, you have the lowest bits. Log2 of the size of the cache block becomes the byte in block that I said earlier. The next m least significant bits are reserved for the index bit, and the formula is simply log2 of number of cache set. Why log2 of number of cache set? Because you can then tell all the unique set number. The rest are the tag bits. The rest are the tag bits. So basically the process is get the index bit. Then you compare the tag bit. So hopefully, if I give you the content of my cache, including the tag store, the data store, you can then operate that cache given different addresses. Basically, these are how. And let's go through some of the basic design. Again, this is like a textbook cache design. A cache block in a direct map cache. This is a unique cache design called direct map cache. What does direct map mean in English? It means that you're going to directly map a cache block to one location. It means that a cache block can go only to one certain set, and inside that set, that's only one cache block. So basically, this means that one cache block per set, one cache block per set. That's the direct map cache. So a load and store look up the tag using the index bit. The index bit becomes the tag. because it's mapped to a certain set. And then you compare the tag, the rest of the tag, if it's match, a hash hit, otherwise it's cache miss. If it's hit, return the corresponding data, otherwise you go search the next level of the cache. And question, if I have the direct map cache, is it possible to get a 0% cache hit rate? You never hit in the cache. The answer is yes, but let me give you some example. Let's say I have 8 sets in total. Can I get 0% hit rate with 9 unique accesses in the loop? You loop through 9 addresses. Can I get 0% hit rate? And tell me how. I'm gonna give you maybe 3 minutes while I'm snacking. Sorry, I'm hungry. If you have an answer, just tell me how.
The last one. This is very zero can resolve of a set.
Yeah, something like that. My next question, can I do this with 2 unique addresses?
The 2 unique access is 100% hit rate.
It's actually doable. So if you have figured it out, let me know. Let's say both of my access go to set 1. Let's say both of these different address go to set 1. What happened? Let's say you have 8 sets right here, and this is set 1. You have access A and B. A, B, A, B, A, B, A, B. Those are 2 different addresses, so they have different tags. Right? The first time I access A, I put A in here. Then I access B. B kicks A because there's only one cache block. Right? So B kicks A. Then you access A, but A just got kicked by B. What's in the cache is B, so you access A, cache miss. A then kicks B, but then you access B, kick A back. Right? So you never have a cache hit in this case, even with just 2 accesses. So another way you can utilize the cache is to have more than 1 cache block per set, right? So hopefully the case that we showed earlier doesn't happen. This is called set associative cache. You can have data access that are mapped to the same location over and over and over and over again. So a solution to this is, well, have a tag store contain a set of possible data and make sure the cache contain more than 1 cache block per set, right? Cache set now contains multiple cache blocks. And this is basically called set associative cache. A 2-way set associative cache means that there are 2 cache blocks per set. So n-way set associative cache means that there are n cache block per set. So that's the terminology. Whenever you say n-way, 3-way, 4-way, 5-way, 6-way, it means many cache block per set. The downside, as I said earlier, if there are way too many cache blocks, you're going to have to compare a lot of things. When you have to compare a lot more things, that becomes slower because you need to compare the first tag, followed by the second tag, followed by the third tag, followed by the fourth tag, right? So this can become slower. A full-blown different design is called fully associative cache. Anyone want to take a guess what this is? Fully associative cache. It means there's only one set. Everything is in that set. Basically, a cache block can be placed anywhere. A lot of search, obviously, because everything is in the same set. When would this work well? And when would this a bad idea? Right? Think about it when you program. Do you prefer a direct map cache? Do your program prefer a two-way cache or four-way cache? Or do you program in a way that you might want to have a fully associative cache? If you go this far, maybe you want to reconsider how you reuse your data, because a lot of the cache design you get from the CPU is like 4-way, 8-way, 16 ways. You typically don't have the fully associative cache. So we talk about how to search the cache. The next step is how to put the data in and how to kick the data out. Direct map cache is easy, right? There's only one cache block. So if you replace that cache block, the new one comes in. There's no policy regarding how to insert and how to replace. But in the set associative cache, you have the design decision. You have 2 cache blocks, 4 cache blocks, 8 cache blocks, for example, right? So you have a choice. Which one do you want to kick out? And these are the key issues. Insertion means that when I bring something in, how do I manage that new block? Promotion means that if I access the cache again and it's a cache hit, do I promote them somehow or do I make them stay the same? Eviction means that if I look at all the cache block in my set, which one do I kick out? And the eviction is tied to what we call the cache replacement policy. You replace a new cache, the old cache block by the new block that you just brought in, right? When the cache is full, you need to kick something out. You need to kick something out, right? And this is called eviction policy. And these are some of the possible design choices, right? You can kick it randomly. You can pick a cache block at random. You can do first in, first out. The first cache block that comes in is the first one that gets kicked out. Least recently used, basically you look at all the cache block and look at which one of these has been accessed the furthest away, and you kick that one out. Not most recently used is basically just don't touch the last access cache block. The rest, random policy. Least frequently used, you basically have a counter that tracks how many of these cache blocks get access and you kick the least frequently used one. Or something like not likely to be used again. Then the question would be how do you predict that? Or some hybrid policy, right? And the question is what is optimal? And this is a big question actually. So you can make a bunch of arguments based on the program that you see on different of these policy, and you can always argue that something is better than the other. So let's talk about the common ones. The common one is recently used or the LRU policy. This is basically based on what we found so far, temporal locality and spatial locality. Why is this tied to recently used? Anyone want to take a guess? Because if you just access the cache, temporal locality tells me that you probably would like to access them again. Spatial locality means that if you access this word, is probably you're going to access the word next to you, which is still in the same cache block, right? Because cache block contains multiple words. Let's say you just access the first word, first byte, then you are likely to get the second word, then the third word, which are all in the same cache block. So the benefit is likely to be effective. But the downside is to implement this in a 16-way, 32-way associative cache, you need a lot of comparator, and you cannot afford to have that many comparators. So the cost is high, right? The cost is high. You can't easily implement a FIFO queue in hardware, to be specific. But you want something like an LRU because it makes sense, right? So you all agree that the least recently used policy makes sense in a way that if you program normally, there'll be spatial and temporal locality. So LRU makes sense. You want to kick something that you haven't accessed in a while out and keep the rest in. So a lot of research about 15 years ago and 20 years ago goes into how do we approximate LRU. Because we say LRU is good. LRU is good. But it's also costly to implement. So how do we approximate this? One way to approximate is tag which one is the most recently used, but you only need 1 bit for that. The last time you access this block, set it to 1, the rest set it to 0. Super easy. And then kick whatever block that has a 0 value. Okay. Or you can have a hierarchical mode, not the most recently used design. Something like this. Let's say you have 4 cache blocks. The first cache block, second block, third block, fourth block. And you hierarchically divide this into 2. Cache block 0, cache block 1, cache block 2, cache block 3. Right? Then you first compare, this is the MRU bit, most recently used bit. If it's 1, if this is 1, it means that between cache block 0 and cache block 1, cache block 0 is the one that you last touched. So between cache block 0 and cache block 1, which one do you want to kick out? Which one do you want to get rid of? Cache block 0 or cache block 1? Cache block 1, right? Because it's not most recently used. Over here, let's say this is 0 and 1. Then you're going to kick cache block 2. Then what you do is add 1 more bit. MRU for the global level, right? And then because it's global level, let's say this is only 0, 0, 1, 0. Right? In a global level, then you compare between each of these hierarchy. This is 0, this is 0. So you haven't really most recently used it, so it's okay to kick one of two, randomly kick one. Another way you can do this is maybe, not maybe, let me erase this. Another way you can do this hierarchy design is something that represent the second bit here, represent between cache block 0 and cache block 2. So this will be 1, this will be 0. And then cache block 3, this is 1, this is 0. Right? Over here, the bit is 1 here and the bit is 0 here. So we're going to kick cache block 2 out. Basically, it's a pairwise comparison between the two groups. And you compare the two. If that's 1 and 0, you kick the 0 out. If it's 0 and 0, the same thing. Kick the 1, kick either one. If it's 1 and 1, also the same thing. Kick either one of those two. It's fine because it's at least not the most recently used. So these are the hierarchical design. Even with this, even with the LRU design, we still need to talk about one big problem in caching, which is called set thrashing, right? What if there are too many data mapped to the same set, right? And here's the example. Let's say you have a 4-way cache. There are 5 access, A, B, C, D, E, going to the same set, and you go A, B, C, D, E, A, B, C, D, E in the loop, right? In the loop. This means that LRU become ineffective because let's say A, B, C, D are in the cache and you access E. If you use LRU, what happens? E comes in, right? Evict A. Your next access is what? A, right? Because you access in a loop A, B, C, D, E. After you access E, you then access A. A want to look up the cache. Check, is A in there? Nope. It's only E, B, C, D, right? And if this is LRU, which one of these is the least recently used one?
B.
B. So A comes in, kicks B out, A replaces B. Then the next access is B. The least recently used one is C. So B replaces C. Next access is C, comes in, kicks D out, right? This replace the block. And as you can see here, you get 0% hit rate. Similar to the break map cache, set associated cache also can run into this problem with the LRU policy. Right? So there are proposals that say, hey, maybe we can use a hybrid policy. Use the two policy. This is the paper proposed by Moin Qureshi in ISCA 2006. Basically, he talks about a cache replacement that's aware of the application. If this happens, then you want to do a different policy, and basically the paper talk about we can sample a different cache set and see which policy is the best that give the best hit rate, and you stick with that policy. So it allows the two policy to compete and then sample only a few sets. The rest of the cache set would apply the policy that is the best. Another thing we need to talk about that is common in textbook and also in the world in hardware is what we call Bellidy's optimal. So there's a paper proposed by Bellady in 1966, this is a long time ago, that looks into the replacement algorithm for a cache. Virtual storage computer is a cache. Back in the day, we haven't had a formal name for this, but this is basically a replacement algorithm for a cache. This is assuming that we have unlimited hardware. The paper say that the policy that's the best is to evict the block that is going to be referenced the furthest by the program, which means you have to have the ability to look ahead in your program, right? Which is impossible to implement. But this is the policy that the designer want to get to. Basically, you want to be able to emulate the policy where we're going to bring in and kick out the block that are going to be referenced the furthest in the program. But this is Oracle information, so you can't tell. You can't tell. So you're going to build a policy to simulate and emulate this, right? The one more concern about this is having a good cache hit rate doesn't mean that this is making the program run faster, because there are many more things that can affect the overall access latency of the program execution, right? Think big picture. This is good. Having a cache hit is good. Having low memory access latency is good, but don't screw everything else just to get this. That's the key message, essentially. Now that we talk about the replacement policy and talk about the LIU block, the most recently used block, let's talk about the insertion policy. So when you insert the new cache block, right, you can insert into different position. You can insert into the most recently used position. This will prevent the block from being evicted. You can actually put this in the LIU position. Sometimes you just read the block once, right, and never read it again. So maybe you want to put some of those data in the LIU position based on the program, right? This would make them more likely to be evicted. There's a reference to two policy called RRIP and DRRIP. This is the implementation of the cache insertion policy that looks into are you going to insert in the MIU or the LIU. Right? If you're curious about this, let me know. There are papers that talk about this. There are papers that talk about how to implement this, and there are also attempt to implement this actually in a company. There's also a promotion policy. It's not about insertion. It's not about eviction. It's not about kicking something out or bringing something in. But let's say you have a cache hit. You access the data and you have a cache hit. Do you promote the cache? Do you promote them to the most recently used? Right? Promote them into the MIU position. And this can be done by basically updating the bits, right? If you go back to what's going to the tag store, there's a valid bit, there's a tag bit, that's a replacement policy bit. If you have cache access, do you update that bit, right? Next, we are going to talk about handling writes, but it's half of the class, and basically now it's 1.5 hours into the class, and I feel like this is a good break. But maybe a good point to do a break. Let's talk about how to handle the writes a little bit after the break. All right, so let's do a 15-minute. Sorry, let's do a 15 minutes break. We'll meet at 10:45. Is that okay? If you're tired, go get coffee. If you are not tired and have questions, just you can type in the chat. I'm gonna go when I'm back. I'm gonna go through the questions that you have and address them one by one. All right. Okay, cool. So see everyone in 15 minutes.
มีคำถามมาครับ
อ่ะ
ตรงหน้าที่มันเป็น direct map ครับ
อือฮึ
ไอที่บอกว่า unique access นี่คือยังไงนะคือหนึ่งมันหมายความว่า unique ใน set หรือว่า address
So the question is about when for the direct map cache, when I mentioned unique access, it means basically if you have an address, it will go to a specific set, and in that set, there's only one specific cache block.
so that's all the question.
Okay. All right, so let's come back to the class and we'll talk about how do we handle the writes. So whenever there's a cache block that is written to, you change the data, right? You change the data. And because you have a hierarchy of the cache, right? If you write into the L1 cache, if you write the data into the L1 cache, you need to actually write it down to the L2 and to DRAM to make sure that the data gets updated everywhere. Right? Basically, if there's an instance of the data somewhere, you need to update this throughout the hierarchy. Which means that when you have writes, you have two options. You can do the write right away. Basically, it is called write through cache. If you modify the L1 at the same time, you're gonna modify L2, L3, L4, DRAM. Make sure that particular address throughout the hierarchy has the same data. You propagate, basically, this is simpler, right? Whenever you do the writes, you propagate it down the hierarchy, making sure everyone sees this copy. But this is bandwidth intensive. Why is that the case? Let's say you have address A. You do a write to A, then a write with the different data to A, a write again to A, and a write again to A. You have 4 writes. You have a four writes back to back to back to back. How many times you have to perform this propagation into DRAM? It means that you generate 4 different requests, right, to DRAM. Wow, it might not even be needed, right? So another policy is called write back. Write back cache means that you are writing the data whenever the block gets evicted, let's say from the L1. If you evict that data, you then write the data, the correct updated data to L2, L3, and DRAM. In the write back cache, the way you can tell if you need the updated data is from the dirty bits that we say in the tag. If the dirty bit is 1, you then need to find where's my updated data. Otherwise, you can delay the writes. So in this case, you have write A, basically write to A 4 times with different data, right? If you do write back, there's a high chance that you only do actual write to DRAM only once toward the end, and you save the 3 additional writes. Don't waste the bandwidth. Basically, write back cache is saving bandwidth and save energy. You just flip the dirty bits. If somehow someone needs that data, then you check the dirty bits and then, okay, the bit is dirty, I need to write it back. Otherwise, you delay writing. You delay writing in the case you have write back to back to back to back. When you have a miss on a write, basically it's a store instruction and it's a cache miss. You also have choices. Do we allocate a cache block and then write it in the cache, or do we just allocate on the miss? right? On the write mess. This is simpler. Basically, write treat it the same as read. You always allocate a cache block. You don't. You perform eviction. You bring in the data, and this allow you to consolidate writes to multiple level. You can also choose to skip the cache completely. You say, hey, I'm writing this to DRAM, and then I don't put the data in the cache. You basically bypass the cache. These conserve the cache space if you know that the write is not going to be used again. For example, you just finish working with the data, you just want to write the result back to DRAM, and that's it. That's the only thing you have to do. Maybe bypass the cache. Otherwise, you're gonna trash the cache, right? There's no need to put the data in cache anymore because you know that you're not going to use it in the future. There are quite a lot of work also to talk about the cache bypassing policy. Over here, one of the reasons because it introduced additional thrashing, and if you don't have to write into the cache, don't do it. So the point here is whenever you think about these policy, you have the option to design. The option to design is governed by how you write the program. How many people use Docker or Cloud nowadays? I mean, among the three of you, how many use them before? You have used them one way or another before, right? Those function as a service or Docker or container. They changed the trend of how you use the cache. So I expect that with this emergence of cloud, emergence of function as a service, the way you design the hardware has to be different. In fact, I'm actually kind of looking into this a little bit, and there's already a bunch of paper in the last year. Actually, it's that recent, right? In the last year that do some study and shows that it has some pretty adverse effects on certain parts of the hardware, and it can contribute to some of the potential slowdown that you see when you use Docker. Now that we talk about cache miss, and we're done talking about read and write and lookup and replacement, right? Let's talk about different types of cache miss. This is more important toward the programmer. When you program things, you want to program your code in a way that you avoid cache misses, right? Because you love cache hits. Cache hits are fast. There are three types of cache misses. Compulsory miss. Basically, this is the first time you see the data. There's no way you can actually bring them to the cache for a few techniques, but this is called compulsory misses. You can use prefetching. We're going to cover what is prefetching in the future, but basically this is the data seen for the first time. They're not in the cache. There's also a conflict miss. A conflict miss is what I showed earlier in the case A, B, C, D, E. Whenever you still have a space in the cache, but it just happened that your data maps to the same set. And then you rotate through that data. They evict each other. So better cache management policy or better programming can help with the conflict miss. Capacity miss is when you just run out of cache space. For example, machine learning is actually suffering a lot because of this. Because the working set is too large, you cannot cache them. The cache become too small to cache everything. So you might need a better management, or you might need to write a better program. A program that utilizes the cache, right? And the way you measure performance of the cache, like the way you measure the performance of your cache, the first thing you can do is to look at hit rate. What is the hit rate? The hit rate is basically if you look at all the cache accesses, how many times you hit in the cache is a ratio, right? For each level of the cache, you can look at the hit rate. You then want to look at the cost of each cache hits or miss, right? If a cache hit is 3 cycles, it's going to be faster than the case where you have a bigger cache and the cache hits is 10 cycles, for example. The total cost of a load is another important factor. Let's say you have to do 100 data load at the same time. So the total cost is essentially on average across that 100 loads. How many cycles do I have to wait? Right? So this is the aggregate load latency divided by number of loads. And to improve the performance of your cache, right? There are multiple things you can do. You can improve the hit rate or reduce the miss rate. They're the same thing by increasing associativity. So increasing associativity generally lead to more cache hits. You can manage the cache better. You can do a better replacement policy, or you can prefetch. Prefetching means that I know that I will need that data for sure. I know that I'm going to load that matrix. So I'm going to get the data ahead of time. Then you can actually send a prefetch command. In ISA, there's a prefetch command to say, I think I know I need that data. So if the CPU is available, go get the data ahead of time, put them in the cache. You can even prefetch into certain cache level. You say, hey, just put that into L2. Don't flush the L1. Don't trash the L1. Put the data into the L2 or L3. You can reduce the miss latency by adding cache level. You can prioritize some critical data. Basically, identify this data load is really critical to my performance. Then I want to make sure that data load is faster. You can do sub-blocking. Sub-blocking means that I'm going to change the granularity of how I manage my cache. Instead of doing a cache block granularity, now you replace just a fraction of the cache block. There are techniques to do that. You can have a better replacement and insertion policy. You can allow more cache misses to be processed in parallel, allowing multiple cache accesses at the same time, right? So these are the things that you can do to improve the performance of your cache from the hardware side. From the software side, you can, for example, break down the problem into a smaller problem where a smaller problem fit in the cache. It means that you can divide and conquer, and hopefully when you keep dividing and conquering, that sub-problem is still in the cache. So when you merge them together, you get the solution, the exact same solution, but much faster. Yep, my cat just hit the off button on a video. Can you hear me still? Okay, it hit a few random keyboard buttons, so I'm not sure what button she hit. So let's go through some example of how the cache latency affects the performance. Let's say L1 cache take 2 cycles, L2 take 5, DRAM take 25 cycles, and you have 100 loads. L1 hit rate is 80%, L2 hit rate is 80%. How many cycles does it take? I'll give you 5 minutes on this. All right, do you have the answer?
400.
You forgot the L1 part. Basically, it's 600, but if you think about it this way, there are 4 accesses to DRAM, right? 20 access to L2, and then every single one of these load will access L1, because you first access L1. If it's missed, it's go to L2. This is 200. This is 100. And this is 100. And I did a calculation wrong. Sorry, 400. All right. So yeah, 400. You're correct, Lucas. I'm sorry. So 400 because you have 4 access to DRAM, 20 access to L2, and then 100. Every single access has to go to L1. Right. So that's 400. Let's go with another example. The same behavior. Now you're loading 1,000 things, right? A lot more loads. You change your algorithm, but now you have 99% hit rate in the L1. What's the hit rate? How many cycles does it take to finish this program?
Yeah, 2100.
Yep. So there'll be 10 of this, and then there'll be 2 of this. So this is 50, and this is 50, and then this is 2,000. So that's 2,100. Right. One last example. Now it's only 10 loads, but it's really crappy hit rate. I'll just do it here. So 10 access here, 5 access here, and then 40%, that's 3 access here. So that's 75, 25, and then 20, right? So this in total is 120 cycle. So to improve the program performance in general, you want to reduce the miss rate. But as the example show you, and I have earlier, if you rewrite the program, then you end up with order of magnitude more data load. That can be bad as well, right? depending on what you're looking at. But to reduce the miss rate without bumping the number of data accesses by the order of magnitude, these are things you can do. When you loop over a large range of data to perform some tasks, subdivide them into chunks, do the task in smaller chunks, typically they would hit in the cache a lot more with the same number of accesses. For example, if you have to multiply metrics, right? What is the common modern day program that do metrics multiply? Machine learning, right? They do tons of metrics multiply. If you load just a fraction of the metrics and do the multiply, and then the next fraction, and then the next fraction, you can do that. That would get you a much better cache hit rate. With that much better cache hit rate, your program would become a lot faster, right? One thing to remember, one cache block is multiple words. So if you access the data word by word, you're gonna have multiple cache hits. If you access block by block, it just and if they just happen to map to the same set, you're gonna have a lot of eviction. So when you access your data, think about the size of the cache a little bit. So there's a Linux command to print the size of the cache, the associativity of the cache in the Intel processor. I actually forgot the command name, but basically you can Google that. When you type in that command, it would actually print out the cache statistics. So you know the size, you know the data word, you know the set, so you know how they map. In high performance computing, where they build API and library, and they build those API and library that you're using, a lot of time they actually have to hack these things. They actually fine tune the accesses so that you get almost always really good cache hit. You can reduce number of memory accesses as I showed earlier. With 10 accesses, it's a lot faster than 1,000 accesses. What happened in modern libraries that you use PyTorch, TensorFlow, the CUDA Blast, like all those libraries that you call and love. If you are at the point that say, hey, this library sucks, I want to keep it, make it better. A few of the things that they do is they would find a way to squeeze out performance, right? So in a high performance computing area, the community basically look at the processor. And then based on that processor, they will have a different policy on how they access the data, because the data access is so important to program performance. So they modify your library calls basically into sub problems so that they map the best to that piece of hardware that you're running on. The problem with these kind of thought, not the problem, but let's say you are just random developer and you want to use the API, and somehow you buy a new piece of hardware and the API isn't fully support that yet. It means that you need to know some of these things to basically go and hack the API, right? So knowing some of these information can help at some point in your career. And cache hit, one last thing I want to tell you for the caching lecture is cache hits really matter for performance. So that's it for the caching part. Actually took a lot more time than I expected, so I'm going to briefly go over virtual memory and then we'll continue on in the next lecture. So what is virtual memory, right? Basically, as I said earlier, you want unlimited memory. You want to have the virtual view of your own memory too. As I said, think about, let's say you have 10 applications running in parallel. You don't want to think about what are the other applications using in terms of their memory allocation, right? Programmer should not have to worry about where each other process usage of memory are, except if you're in the embedded processor area. Sometimes you have to hack the kernel to actually manage that yourself, because memory is way more limited than what you have in the typical desktop or typical mobile phone or even the server. The second thing that you have you want actually is called memory protection. Think of it this way. Think of address as your home address, right? You probably don't want any random guy to come into your home, right? And read the data, read whatever, look at whatever inside your home and modify the content of your house. That's the same thing as memory protection inside computer. The process owns the data, so it doesn't want any random process to go and read or modify the data. Whatever data is in Chrome, it's probably not good to share that with Microsoft Word unless they are actually legit sharing. What exactly is virtual memory? It's let me put it this way. Whenever you have an address, a pointer in C, some data location and array in Java, those are address. They are actually related, associated with the actual location inside your DRAM, right? The location in DRAM is a physical address. The location, the pointer that you see from the process, that's the virtual address. Which means that from the programmer point of view, you only have access to the virtual address. From the hardware point of view, you need to somehow map the virtual address to a physical address. Right? So our job, or at least the content of this part of the lecture and tomorrow, not tomorrow, next week, is that how do we provide that mapping such that you can run any program in your computer and it would work, such that you can have sharing across different programs, such that you can have protection, making sure program 1 cannot access program 2's data. How to make sure that you see unlimited memory instead of whatever you have in your DRAM. Instead of 16 gigabytes, you can actually have 10 programs, each of them use 5 gigabytes. With that, it means that in total you actually demand 50 gigabytes, but in the computer it would run. So first of all, the first benefit is, as I said, each application has access to only their own virtual address space, right? They only see the allocation that happens inside the application. They don't see what else are in there. The second benefit is to have the unlimited memory. And the techniques that we do here is, we call it swapping. Basically, technically your memory is limited, but the page, the data that you're not using, put that in the hard drive. Not a lot of time you have to access to the entire 10 gigabytes of data. Your program would process data one chunk at a time. So the one that you're not using, move them to the hard drive. Right? So the virtual memory management system actually performs this task. You maintain the frequently used data inside the main memory. The rest can be swapped to hard drive. So that's the second benefit. The virtual map to a much bigger space using what we call a page table structure. We will actually go through that detail on how that's done. One terminology that I want you to understand. Whenever I talk about a page, it's a range of address. Typically in the modern day computing, you're looking at a range of 4 kilobytes. Sometimes this refers to a 2 megabyte page. This can be much larger depending on the program and the setup. Sometimes they demand large page. Sometimes they demand a normal 4 kilobyte page. A GPU is actually like 16 to 64 kilobytes, for example, based on how they figure out this is the trend of the program running on each hardware, and they change it based on demand. The page table is what we use to provide the way to map virtual to physical address, right? So basically to determine the physical address, you go through page table. This technique is called indirection. It's a pointer to a pointer to a pointer, which hopefully at the end point to the right location. It's organized in a tree-like structure, and all the page table are stored in the memory. So in Intel x86, you have D-safe, you have 4 levels of the page table. There's a root that is stored in the register called CR3 register in the first level. It tells that's the beginning of your process. Go there to that address. There's a table there. Use part of your address as the index bits. The virtual address and the data from the first level structure point to the second level, and you have this tree of translation. This process is called page walk. We'll go into the detail next week, basically. This is just a wall of text. What I want you to get out of this slide is when you have the virtual address, you need to perform what we call page walk. Go through the page table structure to get the physical address. I'm going to skip the example because we don't have enough time to cover the entirety of the current lecture. So let me skip to here. Basically, now that we don't have time to cover the rest of virtual memory part. How I guess last 3 weeks paper. Now that we are back to the post midterm mode, anyone want to present their paper review, or should we do it later? I think each one of you still owe me like one more presentation. And it can be, you don't have to make slides, basically. If you already have what in mind and the discussion in mind, we can talk about it right now. So anyone want to do that, or do you want to skip to the next week? We have time. We have time both this week and next week and the week after.
I can take a look because I picked, I think 2 weeks ago, the paper about slave memories, but I have to open my documents first.
Yeah, sure. So let me stop recording because that's pretty